Hello? Hello? Am I
Sir,
audible?
yes, yes, sir.
Oh,
Yes.
okay. So this is the table that what we have done. We have proposed 10 comparators and we have compared with from this we have to find out which design is much more accurate, which design fulfills our design criteria and which will go to ultimately go to the chip. So the parameters we have decided, that is number of transistors we have used, then the delay, how fast the circuit is, the offset voltage, ICMR and power dissipation.
Gandhi, sir,
So
your
if we
slide
go
is,
by this, yes, yes,
sir,
sir.
your slide is not showing. Yes, now it is showing. Screen sharing. Yes, sir. Yes.
Showing now.
Okay.
Okay.
Yes, sir. Yes.
So total 10 comparators has been proposed. So from these 10 comparators, which design is much more superior? So how to find that design and how to take this design ultimately to the chip? So we have given the five criteria: the number of transistor used, the delay, the offset voltage, the ICMR, and power dissipation. So from this we can find out that last comparator PC10, that has been given the name a fully differential double tail dynamic comparator 4. That is a 13, total number of transistor used is 13, delay is 0.24 nanosecond, offset voltage is 0.11 millivolt, and ICMR range is minus 0.50 to 0.57, and power dissipation is 216.37 microvolt. So we can find out that this is a much more superior comparator among all proposed comparators. So we have focused on this PC10, that is FDD TDC4. So this is the layout of FDDC. This is how the chip is going to be prepared. So first we have to prepare the layout, and this layout, from this layout we have to generate the GDS file, that is convert data stream or graphical data stream. That file we have to send it to the foundry. There is no foundry exists in India at present. So let me clear that on that. So we have to send it this foundry GDS file to the foundry, and foundry then going to prepare the chip, and that chip into there in a. So the area occupied by the FDDC, that is fully differential dynamic comparator, is 16.5 micron meter into 17.6 micron meter. That is height and width. Similarly, layout this layout has been prepared in a mentor graphics. Another tool we have used, that is Cadence, to get that better result and better accuracy and to find out any bug. So this is the layout prepared in Cadence. Now, if we go into the layout of FDDC 4, that is final PC10 proposed comparator, then that is our ultimate design. The area occupied by the comparator is 15.03 micrometer into 17.8 micrometer. Again, layout in Cadence, and this is the layout of buffer that I have already told you to. We have to convert it two-ended output into a single-ended output. So that is 13.1 micrometer into 14.7. So what is the outcome of this? So this is actually the pre-layout simulation. There are in electronics, whenever we are dealing with the chips, there are two kind of simulation we carried out. One is the pre-layout simulation, and another will be the post-layout simulation. So these are the in paper you will find out that only they have been concentrated on only few parameters. But now we can see that I have listed down almost many parameters which has been not there in the literature, including the noise spectral density, CMRR, power, PSRR, power delay paradox, and FOM. So from this also we can find out that PC10 is much more superior comparator as far as all the comparator exist in references, and as far as the other all proposed 10 comparators. Now we go to the Monte Carlo simulation. That is, this is the Monte Carlo. Why we need Monte Carlo simulation? Get that accuracy, how accurate your result. For that, any of this Monte Carlo simulation is not you cannot specify to the any field. It is applicable to all the streams. It can, you can, if you are from mechanical, electrical, civil, computer, to get the how accurate your result, how accurate your system, you can carry out the Monte Carlo. That is the number of trials you carry out. You can say the number of iteration. For that you have taken the simulation. So, and parameter you can choose anything. Here I have taken the parameter of offset voltage, and this graph is named as a histogram of FDDC, fully differential dynamic comparator. From this we can find out that absolute value of offset voltage is 4.1 milliwatt. That is this absolute value from this. And the deviation, standard deviation, that is bell-shaped curve Gaussian, that is 2.49 milliwatt. That is for FDDC, that is our reference comparator. And this is all installed for all comparators. So if we go into this last for FDD TDC4, we can find out that absolute value of offset voltage is 0.36 milliwatt. It is very less as compared to all other 4.8, 0.72, 0.61. Here is 0.36. And standard deviation, that is also accuracy is concerned. So we from this also we can conclude comparator, and that can go into the application. These are the some of the analysis that we carried out for various, but we will go escape this. That is the supply voltage, and again it is the delay versus temperature. We know that or any design has to work any of their either space, desert, or you can in a Himalayas or where the cold. So it has been from minus 25 degrees centigrade, 5 degrees centigrade, and we have seen which comparator will give you the much more better accuracy. So again, FDD 3DC4 is more accurate as compared to all of them. These are again been carried out. The transistor will give you the more accurate. These are the comparison. This is again transistors that we use. FF means fast, TT means typical transistor, means slow and fast, and SS means slow.
Hello, Gandhi sir.
Hello, I think there
Sir.
is a problem with the internet.
Yes, sir. Don't worry. Goodbye.
Okay. So this is what the final ultimate pre-layout and post-layout simulation what we have achieved. So here we have achieved 1.3 giga sample per second. Our desired specification to achieve 1 giga sample per second. So here sampling frequency we have achieved is 1.3 giga sample per second. So now what are the observations from this design? So that is the most important, as and when we do any kind of analysis or any kind of research, we should find out some specific observation, what are the findings. So these are the findings. So actually in comparator there are two kind of design, differential design or double tail design previous to this work. So again the design of tail transistor will give you the how good your comparator. Then the why, because it will limits the current flowing through the output branches. So how good you have designed the tail transistor, that is give you the ultimately the speed. Then we have to separate out the input gain stage and output stage, because otherwise it will have the effect of noise on output stage due to the input stage. And again we have to reset the circuitry after each and every comparison. Again the circuit should go into the reset mode for the next comparison. So how we reset our circuit, or how we are going to reset the decisions, previous decision, that is also the going to affect the accuracy, because it is going to be considered as a previously code dependent errors. And for low offset there should be less stacking of transistor between input transistor and tail transistor. So in bottom we should have less number of transistor. So in summary, the conventional comparators, the mismatch between cross-coupled circuit determines the trade-off between speed, offset, and power consumption. The modified existing architecture, and we have proposed the 10 architectures. And 10, all 10 architectures has been characterized for propagation delay, ICMR, gain, phase margin, supply voltage, mismatch analysis, process variation, supply voltage variation, temperature variation, and from that we find out the promising architecture. So ultimately we have seen that previously to this design there was a single concept, that is either you go by differential comparator or either you go by double tail. But here we have mixed both the concept into a single design. Our design is fully differential, also design is double tape. So from that we can find out that FDD TDC4, that is our last comparator, that is ultimate comparator, is 45% more faster and 30% more power efficient with very low offset as compared to the conventional comparator which we have compared. The core layout occupies an area of 267.53 micron meters square. So FDD TDC4 has the resolving capability of 1 milliwatt. It will detect the difference of 1 milliwatt difference and result into the 10-bit resolution. So it will convert that up to 10-bit for ADC. So Monte Carlo simulation confirms that FDD TDC4 has the offset voltage as low as 0.36 milliwatt at 1.3 gigahertz speed while dissipating the power of 265.25 microwatt. So again, what we can do in future. So the proposed FDD TDC can be optimized for the minimum offset voltage and maximum speed at limited area. So this again we can do something so that we can reduce again the little bit offset and we can increase the speed. This concept can be taken into the other design also, future and past design, and that it is applicable for the consumer electronics and the IoT also. So because IoT also needs to compare the signals. So ultimately it is again analog to digital converter. The proposed architecture can be further implemented in lower technology because present VLSI, it is a 22 nanometer technology or 18 nanometer technology is there. We are designing 180 nanometer technology. So we can do this again in a lower technology to get much more superior result. So these are the references. Actually, there are many more references, but these are the things that what we have put in a presentation. So, any question, I am ready to take any question, any doubt, and I'm sure that I am very much clear what I have discussed. Yes,
Yes, Gandhi sir.
yes, sir.
Really, your lecture is really inspiring for us.
Yes, sir.
Actually, sir,
Thank you.
I have some simple doubts. These
Yes, yes. Go ahead.
comparators. Okay.
Yes,
So,
yes, yes, yes.
is it possible that this comparator has some startup idea?
Definitely, it can be patented. But now this is already published work. This
Okay.
comparator ultimately go into the system, and we have to fabricate the chip, right?
Okay.
And there is no fab lab exist at
Okay.
presently in it.
In
So
India.
this is very difficult because of fab lab it will cost in a billions of dollars. So
Hmm.
there is no in India. That's why there is no fab lab in India. So we can design the soft part that we can take it into the we can have the establish the company and we can do this kind of soft part, but ultimately we have to send it to the some foundry and
Hmm.
then they are going to fabricate the chip.
But your idea is very much clear, and
Yes,
also
sir.
from this idea, I have some innovative idea. So definitely,
Yes,
sir,
sir.
I will talk with you because
Yes,
in
sir. Yes, sir.
startup is concerned,
Yes, sir.
uh, you don't find any kind of good startup in this comparator. Okay,
Yes, sir. Yes, sir.
so some of our students are working on comparators. So if they have
Sure,
some
sure.
doubt, so definitely we will contact you. And if
Sure, sure.
possible, and if possible, if you will apply for patent, so
Yes, sir.
definitely we will put your name.
Sure, sir.
Okay,
Thank you.
sir.
Thank you, sir.
Gadi sir, thank you very much. And we wish that in future also, if any need arise, you will help us. Thank you very
Sure,
much.
sir. Sure. It's my pleasure. Okay, sir.
Thank you.
Any question from participant?
ML Patel sir. Okay. Okay, Gandhi sir.
Okay.
Okay. Thank you
So
so
should
much.
I close?
Yes, sir. Yes.
Okay. Thank you. Hitesh sir, just send me the recording of this. You can share it with me. Okay.
Sure, sir. Sure, sir. Sure.
Okay. Thank you. Thank you. Thank you.